Hi, welcome to 2.2 derivative formulas. We've looked at the real basic formal definition of a derivatives, but today is about like how we can like kind of narrow this down and look at it in other ways. So some shortcuts is what we're going to be looking for determining these derivatives today. So this is a first alternative form of a derivative. It's a little bit pared down. I mean, it's not a lot, but it is at least some. It doesn't have the delta x anymore. It doesn't have the h. Instead, it's taking those two y values, same idea of a slope, because a derivative is just the slope of a tangent line. So we want to check this slope. So as the original x value is getting, the amount of change is getting smaller and smaller, as this c value gets closer and closer to 0, as x and c starting to match up, then we're going to get that nice same instantaneous slope, because this is basically a slope thing, and we're just making the space between the 2 points of a secant line closer and closer together until they're right on top of each other, and then boom, you've got yourself a nice derivative. One thing you need to be careful about with this one is it gets rid of, you lose a little bit of that limit on both sides. So you need to make sure that you've got those two limits so that as x is approaching c on the left and right, just like any good limit, you want to double check, hey, do we have good limits on both sides? And are these two limits equal to each other? This limit has to be the same as the other limit. We talked about last time how if you had these two limits, they're good limits. Oh, that's great. But if they're not equal to each other, they're not meeting up, then we're not going to be able to get a good derivative there. It's discontinuous. If it's discontinuous, we're not going to be differentiable. All right, so we want to find the derivatives from left to right at x equals 1. We've got to check to make sure those exist. And then we're going to use that to determine if the function is differentiable at x equals 1. Now, we already know that it's not, but we're going to show why it's not using this new definition of a limit. Now, we know this is already not going to be differentiable at that point, because we can kind of like picture that graph. So we're checking out when the absolute value, x minus 1. So if we kind of just move that graph over a little bit, here's our graph. Boop, boop. And there's our point at 1. And that is one of those sharp points that we were talking about last time about like, hey, that is not going to be differentiable at that point. I want to use our new definition for our derivative in order to show that, but I already know, yeah, it's definitely not differentiable there. So, but let's show it using that left hand and right hand limit. So if we start on the left hand side, I don't know why I used a cursive L. I want to check the limit as x approaches 1 from the left of f of x minus f of 1, because that's the spot that I'm checking. I'm doing f of 1 because I'm checking the limit at 1, the derivative at 1, and x minus 1, because again, our c value is 1 for this case. So that's the limit as x approaches 1 from the left of f of x, which is the absolute value of x minus 1, minus the absolute value of 1 minus 1, all over our x value, which is just x. I don't know why I was changing that. X minus 1. So in our numerator, we've got this absolute value of 1 minus 1. Well, 1 minus 1, that's 0. Absolute value of 0, that's still 0. So that whole thing is just 0. So that thing's just sort of gone. So this is the limit as the absolute value of x minus 1 over x minus 1. Okay. Now, we want to kind of imagine we're coming in from the left-hand side on this thing. So we're coming in from a number like 0. We can't actually put 1 in there, and we can't simplify this thing down anymore because the limit doesn't exist at that point because it's having all these problems. So we want to kind of imagine, okay, we're just to the left of that thing. Where would we be like if we were just to the left of 1? Well, that would be a small decimal number. So a small decimal minus 1, that's going to be like some negative number. And then in the numerator, we're going to get the same thing, but it's going to get absolute valued. So it's a positive version. So we'll have the same goofy decimal number over each other, but one will be positive, and the denominator will be negative. So this limit, it'll end up being about negative 1. You can even see that too with our graph. We can look at that absolute value line and we know that slope. It's just heading straight down. It's negative 1. That's how absolute value graphs work. So we know the slope was negative 1. There, we're just able to see it using our cool new definition of a limit. Let's check the right-hand side. If we go to the right, everything's the same, except now we're checking when x is approaching 1 from the right-hand side. So we're still going to do f of x minus f of 1, because we're going to still check at 1. And we've got x minus 1, because that's what we're checking, x minus 1. So this is the limit as x approaches 1 from the right of our absolute value of x minus 1 minus our absolute value of 1 minus 1, because I'm doing f of 1, and the other one was f of x, and we still got x minus 1. So this is the limit as x approaches 1 from the right of the absolute value of x minus 1 over x minus, not plus, minus 1. Because this thing is going to turn out to be 0 again, in case you didn't already guess that. Now, again, we can't put in 1 there. We can't do anything else to simplify. Some of the PDF notes, when they do simplify down, so we're able to get some nice values, but we're not able to get it this time. So we're going to have to use our heads a little bit. We're going to be just to the right of 1, so I'm going to have a slightly bigger number. Let's use 2, because that's easy. So I've got 2 minus 1 in the numerator. Well, that's 1. And I absolute value that, and that's still 1. And then I go to the denominator, so 2 minus 1, that's going to be 1. So I got 1 over 1, it's 1. You can do the same thing with like 1.001, so you can actually be really, really close and to the right, but it'll work out to be that same way. So this limit is going to be 1. You can also see that in terms of our graph. If you know your absolute value function, you know that on the right-hand side, it's got a slope of 1. Okay, cool. So now, in order for us to use our cool new definition of derivative, we need to make sure that these two limits are equal. But unfortunately, they're not equal. Negative 1 is not equal to 1, so we can't use our fancy new derivative formula. Since those are not equal, f of x is not differentiable. At x equals 1. Dang it, it didn't work there. And that's fine. It's not differentiable. Even if we had some other formula, which we will in a bit, had some other formula to determine the derivative, it's just not differentiable there. This is also telling us that. So that's cool. So like I said, there are a couple more examples that I do in the PDF notes. It's the same deal, but I break it up a little bit better. And it's got a nice left-hand and right-hand limit because you've got a piecewise function for this one. Everything simplifies down and it's a little bit easier to identify the slopes. Check it out in the PDF notes. It's worth a look. Same thing here. You've got a nice clear left-hand and right-hand piece, and you can check those two pieces and they simplify down, and you can check to see if those two limits are equal to determine if it's differentiable at that point. Great, great stuff. But we've got a lot of ground to cover today, so that's why I'm not going to go into them. I really recommend that you check out those PDF notes. But I'm going to actually use this alternative form. So off to the side, I've already checked. Yep, those two limits exist and they are equal. So I want to find the derivative at x equals c if it exists for this one. All right, so our new function says, okay, do f prime of 3 because that's the c value that I was just given right there. And my new form is I do the limit as x approaches c, but our c value is 3, oops. As normally it would be x approaches c, but it told us our c value. It's 3. I want to do f of x minus f of c, which in this case is 3, over x minus c, but our c value, again, is 3. So let's figure out what that is. So this is the limit as x approaches 3 of our f of x, so that's x squared minus 5, minus our f of 3. So that is going to be, I'm just going to write it to the side here, 4 squared minus 5. So that is 4 squared is 16 minus 5, so that's 11. Now, why did I put a 4 there? It should be 3. How about 3 squared minus 5? That is 9 minus 5, which is 4. Oof. I cheated and looked at my key off to the side there, and I saw that the answer was 4, but then I substituted that value in. Oops. Okay. All right. So now our numerator ends up being x squared minus 9. So limit as x approaches 3 of x squared minus 9 over x minus 3. I'll move these things down and out of the way here. There's another example of this in the PDF notes that works identically to this. Again, I recommend you work through those because there's a lot of good stuff here, but I just don't have the time to make a video for all of it. But you can do it yourself, and then you can use the PDF notes to check yourself before you wreck yourself. As x approaches 3, I'm going to factor that numerator, so x minus 3, x plus 3. I'm going to do factor cancel method for this because these x minus 3s are going to cancel out. So we get the limit as x approaches 3 of x plus 3. Well, hey, we can figure out that limit. It's just 3 plus 3, which equals 6. Okay. So we found the derivative, so the slope of the tangent line when x equals 3, when c equals 3, should be 6. So at that point, we should see a nice slope of 6 for our tangent line. You can do another problem like this out of the Larson books in the PDF text. Highly recommend it. It's worth a look. I'm going to do another example that gives us a slightly different result. So I got the square root of the absolute value of x. Now, hopefully there's some alarm bells of non-differentiability going on in your head right now, but let's say they're not going off. And so we just say, oh, yeah, sure, yeah, that's fine. Well, yeah, let's do it. I'm gonna totally do all that stuff. I'm going to use my new definition of my limit. I want to do f prime of my c value, in this case is 0, equals the limit as x approaches 0 of the f of x minus f of c, which in this case is 0, over x minus 0. Oh, well, that's nice. Everything seems to be going so well in this problem where it's not going to go well. Limit as x approaches 0 of f of x, so that's the square root of the absolute value of x minus f of 0. So f of 0 is the square root of the absolute value of 0. And then in the denominator, x minus 0, that's just x. Okay, so now we've got the limit as x approaches 0 of the square root of the absolute value of x over x. And then you just kind of stop and you say, huh, well, I can't like rationalize the numerator because there's an absolute value in there, and that's just not going to end well for me. So this doesn't seem to be working. I'm going to check out what's going on my calculator here. So I've got this handy thing. Come here. Now that I'm taking a look at my calculator, I've noticed, hey, at 0, this thing is swooping down to negative infinity, and this one's swooping up to positive infinity. So these two are heading away from each other. My left-hand limit and my right-hand limit are not equal to each other. The left-hand limit is negative infinity and the right-hand limit is positive infinity. Since those two limits are not equal, then we are not able to do, the function is not differentiable at this point, since those two limits are not equal to each other. So, dang it, we are not differentiable at x equals 0. Is what we would say for this one. So let's go back. I'm going to write that down. F of x is not differentiable at x equals 0. Bummer. Oh well. If you wanted to see another example of when this breaks down, go ahead and check out these PDF notes.